All right, our final topic from chapter 4 is partial fractions. And this should be a term that you are somewhat familiar with, but it's going to take a little bit of review of that. We're going to use this method of integration when we are asked to integrate some function that is expressed rationally. In other words, it's expressed as a fraction, kind of like we had with long division. But in this situation, we've got two different situations here. First of all, the degree of g of x, the degree of the top, is smaller than the degree of the bottom. Now, when we did long division, we did degree of the top was larger than or equal to the degree of the bottom. So let's see what happens in a situation like this. Now, the theory behind this process of partial fractions is this. If we were to add these two fractions together, we have got 3 times x minus 3. I got to get a common denominator. We'll add 2x minus 4. And we'll divide that by this common fraction where we've got an x minus 4 on the bottom and an x minus 3. So we've got a common denominator. Now, if I were to multiply this numerator out, combine like terms, I think I'd have 3 x's and 2 more x's. I think I'd have 5 x's. You'd have minus 9 and minus 8, so minus 17. Over this common denominator, x minus 4, x minus 3. And so, if I were given the problem, 5x minus 17 over x, let's call it, let's make this even a little more complicated here. Let's call it x squared minus 7x plus 12. We're asked to find the integral of that thing. Well, I don't know what the integral of that is. I'm not quite sure how to handle that. The degree of the bottom is larger than the degree of the top. But if I can break that into this fraction plus this fraction, I think I can find those integrals. I think I can call this 3 natural logs of the absolute value of x minus 4 plus 2 natural logs of the absolute value of x minus 3 plus c. And so the rational fraction can be broken down into partial fractions whenever that denominator can be factored. So we're looking for a situation where the degree of the top is smaller than the degree of the bottom, and the bottom can be factored. And that's going to be a signal that we will most likely be using partial fractions. Right. So a very similar looking problem here, not 5x minus 17, but we've got 2x minus 15 over this x squared minus 7x plus 12 that we saw in the previous problem. And so the first step is to break the rational function into its partial fractions. Well, what I'll notice as I look at my original problem here is the bottom can be factored into the same x minus 4, x minus 3 that we saw in the previous problem. So let's break this into the sum of two fractions. And let's put a over x minus 4. Let's put b over x minus 3. And let's figure out what's the value of a and what's the value of b. Well, what I would do is to get a common denominator in this situation over here is I'd multiply top and bottom by x minus 3, top and bottom by x minus 4, and so I'd have a x minus 3 over this common denominator. I hope you're doing this in something that can be erased. Plus b. And then multiply bottom and bottom here by x minus 4. We have x minus 4. X minus 3. And that is equal to 2x minus 15 over this x minus 4 times x minus 3. I'm never going to write it like this again. I have worked to get the common denominator. And so now that I know the denominators are identical, and in order for this sum to be equal to this side over here on the right, all I need to do is to get the numerators to be the same. So I've worked to get the denominators equal. So in order not to clutter this up, I'm going to get rid of those denominators and focus my attention on getting the numerators equal to each other. That's what I really want. And how do we figure out what A is and how do we figure out what B is? Well, I'll tell you what I'm going to do. I'm going to let x equal 3. And if I let x equal 3, this piece of the puzzle here is going to become a times 0. And this piece of the puzzle here, if x is 3, 3 minus 4 is negative 1, I'm going to have this. And if x is 3, 6 minus 15, so I know the value of b is going to have to be 9. I could use matrices. There's different ways of doing this, but I do believe this is the most efficient way it's going to happen. Now, what if x is 4? If x is 4, if x is 4, b is gone. If x is 4, 8 minus 15, a is negative 7. So this integral right here becomes the integral of partial fractions. A over x minus 4, negative 7 over x minus 4. Plus b over x minus 3, plus 9 over x minus 3. Dx. And that becomes negative 7 natural logs, absolute value of x minus 4. Plus 9. Natural log absolute value of x minus 3. Let's see. Okay. So as long as that bottom can be factored, I'm pretty suspicious it's going to be a method of partial fractions. All right. let's see. I can factor the bottom. Oh, let's see. I think it would be x plus 2, x minus 1. And therefore, let's see, I would have a, let me move this a little bit. I would have a times x minus 1 plus b times x plus 2 would be my numerator once I got my common denominator. So that's going to be equal to my numerator, x plus 5 over that same common denominator. So I've just left out those denominators. Now I'm going to let x equal 1. If x is 1, this is going to be 0. I'm going to have 3 b's. And if x is 1, then b is going to be 2. I'm going to let x equal negative 2. So that's going to be negative 3a. And let's see, if x is negative 2, so a equals negative 1. So, could be yes or done. I know what a is. I know what b is. And so I've got negative 1 natural log absolute value of x plus 2 plus 2 natural log of x minus 1 absolute value. Looking good. Now, one other side note here before we move on to number 6 is, what if I had something, anything, over x cubed plus x squared and we turn that into a minus. Minus 2x. And I had to take the integral of something like that. Well, if I factored the bottom, I'd factor out an x, I'd factor out what was left. You know what this is. This is just x times this. I would have a situation where when I factored the bottom, I'd have x, I'd have x minus 2, x plus 2, sorry, and x minus 1. And so when I form my partial fractions, I would have 1, 2, 3 of them. If I factored the bottom and I got 3 separate factors, I would have 3 partial fractions. I would have an integral. I'd have a over x plus b over x plus 2 plus c over x minus 1. And then I'd have a times x plus 2, common denominator. I'd have to multiply the a fraction by x plus 2x minus 1. I'd have b times x minus 1. I would have c x plus 2. I would again start with, let's say, let x equal -2. Let x equal 1. Let x equal 0. And I would be able to figure out the value of A, the value of B, and the value of C if the bottom factors into 3 factors. I don't think AP would go beyond that. So just wanted to give you a heads up there. Okay, this guy, number 6. So we've got several options here. I can factor the bottom. I can call this 6. Oh, x plus 2, x plus 8, a over x plus 2, b over x plus 8. All right, so a is x plus 8 plus, let's focus on that numerator, b x plus 2 equals my numerator back here. So let's let x equal -8. Let's see, x is -8. I think this would become -6b's. So b, I have to equal -1. Let x equal -2. Let's see, -6a equals 6, so a is going to equal -1. And so what I've got here, since I have figured out a and I have figured out b, is I have got -1 natural log of x plus 2 minus the natural log of x plus 8. Okay, so I don't see that anywhere. Extend the page. It looks as if, let's see, if I'm going to subtract, I could turn this into a division. Let's see.